In the previous lecture, we have discussed about the pulse position modulation, and we have seen the how ppm waveforms are generated from PWM, and also we have seen the detection methods of PWM and ppm signal. Now we will continue again in the pulse modulation, and we are coming under the topic of digital transmission of analog signal. Means we are now going to understand the process of digitization, or the process of converting analog signal to digital signal, which is also called as pulse code modulation. So output of the pulse code modulation will be in the form of digital signals, but this particular waveforms or this particular modulation technique comes under the category of digital transmission of analog signal. So we will understand with the help of this block diagram that how analog signals are converted to digital signals. So when we are converting analog signal to digital signal, it is a three-step process. The first step is a sampling, which we have already seen. We have already discussed the types of sampling, that is ideal sampling, natural sampling, and flat top sampling. We have also seen the pulse amplitude modulation, which is nothing but sampling. The second step in the conversion is the quantization or the quantizing, which we will look now. And another step is nothing but the encoding. So input signal to a PCM encoder, which is pulse code modulation, is the analog signal, and the output of this particular PCM is our digital data, and the digital data is in the form of ones and zeros. So input to the sampler is the analog signal, which will look like this. The sampled signal will be nothing but our PAM signal, which will look like this. After quantizing of the PAM, the signal will be looking like this, and after encoding, the signal will be a digital data. So this is the three-step process which is which is used to convert any analog signal into the digital signal. And now, with the help of example, we will understand that how the sampling is performed, how quantization is done, how encoding is done, and how the analog signal is therefore converted to digital. So now consider the diagram which is shown here, which is nothing but any analog signal which is taken. It is x of t is the analog signal which is plotted with time. So you consider any analog signal of any nature which is looking like this. The first step of conversion into the analog signal, see the axis. Now here it is the time domain axis, which is x of t. Then it is x of t is the representation of signal, the domain is time. Now the first step is converting analog signal to sampled signal, and now instead of a continuous time signal, you will be having a sample which will be represented by n, and now the signal is x of n. So the signal is first sampled at a regular interval, and you should not follow that this particular sampling is done by the following sampling theorem, where sampling frequency should be greater than or equal to twice the maximum signal frequency. So sampling theorem is kept in the mind and the sampling is performed, and now it is no more time axis, it is the sampled axis, that is number of sample, and it is n, and the signal is x of n. The second step after the sampling is the quantization. So now you see quantization process. What we have done is we have stretched a horizontal line from each of the level. Each of the level means they are the amplitude of this particular sample. Let us say it is 0 volt, 1 volt, 2 volt, and 3 volt. So at every stage the line is stretched, and you will be getting a waveform something like this. Now in the next step, we are going to convert our sample into the quantized level. So this 0, 1, 2, 3, this is nothing but a quantization level. What is quantization? The quantization is nothing but a process of assigning a nearby quantization level to each and every sample. So each and every sample, whatever is the nearby level, now this particular diagram we have quantized into 4 samples, 4 levels. So we have 0, we have 1, we have 2, we have 3. These are the 4 levels of quantization, and this is what is the quantization, assigning a nearby values to that particular sample. So now between 0 and this particular sample, there is no sample at all. So 0 will be assigned to this particular level. So you can see this is a red line. 0 will be assigned. Now there is a one sample having an amplitude of 1 volt. So this particular sample will be assigned 1 volt as a quantization level. Then holding. Once it is sample, then it will be hold at this particular level. The next sample comes at the 2 and as nearby. Now this particular sample is not at level 2, it is not at level 3, it is somewhere in between, and that is why what is done is assign a closest level to this particular sample, since it is not near to since it is not 3, not it is 2. Okay, so we are assigning a closest level. So closest level for this particular sample is 2, so we are assigning 2 level for this. Again it will be holding. Then again next sample is between 2 and 3, but it is near to 3, so we are assigning a 3 level to that, and the quantization level will be 3. Again it will be holding. Again the next sample is between again 2 and 3, so assign a quantization level of 2. You can assign 3 also, but you can assign a quantization level of 2, and this is how the quantization is completed. So you can see there is an analog signal, there is a sampled signal in this figure, and the red lines indicate this is the quantized signal after quantization. So the two steps are now clear. Two steps are sampling and another is quantization. Sampling is converting analog signal with the help chopping that into a sampled waveform. Quantization is assigning a nearby levels. So complete waveform we have divided into 4 level, and whichever sample was there at the level we have assigned same, but whichever sample was not there at any level we have assigned the closest level for that. So this particular sample is nearer to 2, so we have assigned 2. This sample is nearer to 3, so we have assigned 3. This sample is exactly between 2 and 3, so you can assign 2 or you can assign 3, but in this diagram it is assigned as 2, and then the entire is completed. This sample is exactly at 1, so it is assigned 1 only. This sample is between 0 and 1, so it is assigned a level of 0, and then the quantized signal is complete. So each quantization level corresponds to unique combination of bits. The analog signal is transmitted or the stored as a stream of bits, and it is reconstructed when required. So now analog signal is no more, it is converted into bits with the help of this particular quantized level. Now since it is the 4 level, so we know 4 level may we can have 2 bit combination. So this particular level I am assigning 0 0. To level 1 I am assigning 0 1. To level 2 I am assigning 1 0. To level 3 I am assigning 1 1. So whichever sample is at 0 will be encoded as 0 0. Whichever sample is at level 1 will be encoded as 0 1. Whichever sample is at level 2 will be encoded as 1 0. Whichever sample is at level 3 will be encoded as 1 1. This sample is at level 2, so it is 1 0. This sample is at level 1, so it is 0 1. And again this particular sample is at level 0, so it is assigned 0 0. So this is the third step of converting analog signal to digital, which is nothing but encoding. So encoding means assigning a level, assigning a bits to a quantization level. Okay, so sampling, quantization and encoding. So here in this waveform all the 3 steps can be seen. This is continuous time analog signal. Then these dotted are the samples. The red line indicates it is the quantized level, and this particular bit stream is indicating that it is a bit stream is indicating that it is the encoded signal. So now your analog signal is the original signal. It is converted into quantized signal, and then it is encoded with this particular bit stream. So now this bit stream will be transmitted, analog signal will not be transmitted. And that is why I have given the title as digital transmission of analog signal. So analog signal is converted to digital with the help of sampling, quantization and encoding. Quantization is assigning the levels to the sample and encoding is assigning the bits to the quantization level. Now, for example, here I am having only 4 samples, so 2 bits are sufficient for the 4 sample. If I have here 8 samples, then I will require 3 bits from 000 to 111. And if I have more number of bits, more number of sample, accordingly I will be requiring more number of bits. Okay, so 4 levels are there. Because of that, 2 raised to 2, 4 bits, 4 levels can be identified with 2 bits. If it is 8 level, then 2 raised to 3. If it is 16 level, then accordingly the levels will get multiplied and the bit stream will be there. Number of bits per sample. What is this 00? 00 is called as 2 bits per sample. 01, 2 bits per sample. So when you have 4 quantization level, you will always have 2 bits per sample. When you have 8 quantization level, you will have 3 bits, 2 raised to 3, 8 bits per, 2 raised to 3, 8 means 3 bits per sample you will be having. So this is our original signal. This is our quantized signal. So there is a difference between the original signal and the quantized signal because we have rounded our sum of the sample to the nearby level, and this particular is called as quantization error. So there is a degree of quantization error, number of quantization level. So it is apparent from the figure that the original signal and quantized signal do not match because we have assigned to some of the samples a nearby level, and because of that the quantization error is introduced into the figure. So how to remove this quantization error? If we have more number of quantization level, then the quantization error will be eliminated. So you can see here there is more number of samples here, and because of that you see your quantized signal and your original analog signal matches. Now if we consider a PCM of the speech signal is analog. If we want to transmit analog speech signal into digital way, then the speech signal is having a frequency generally from 300 to 3400 Hertz. Maximum frequency is 3400 Hertz. So what should be the Nyquist rate? It should be twice of FM. It is equal to twice into 3400, which is 6.8 kilohertz. But the practical sampling rate Fs will be equal to 8 kilohertz. Why? Because number of quantization levels are 256. How you got this 256? Because number of bits per sample is equal to 8, and log of 256 to the base 2, when you take, you will get 8. So now what will be the data rate for the transmission of the speech signal? It will be N into Fs. What is N? N is the number of bits per sample. What is Fs? Is the sampling frequency. So 8 into 8000, it is equal to 64 kbps. 64 kilobits per second is the speech signal, is the rate at which this particular speech signal can be transmitted. Now the bandwidth requirement for speech signal, the communication theory tells us that we can transmit error-free at the most 2 pieces of information per second per hertz of bandwidth, and therefore the bandwidth for the PCM speech signal minimum will be equal to 64 kbps divided by 2, which will be equal to 32 kilohertz, and this is the bandwidth requirement for the PCM signal, the speech we want to transmit. So here we have considered maximum frequency as 3400. According to sampling theorem, Nyquist rate twice of FM will be 6.8 kilohertz. Practical sampling rate is 8 kilohertz always. So number of levels will be 256. Okay, so number of bits per sample will be equal to 8, and therefore data rate will be 64 kbps. For successful transmission, data rate should be half and bandwidth will be 32 kilohertz.